and welcome. My name is Lazarus Ekapidis, and I am Senior Network Engineer here at MORRELL Telecom. We're continuing our series of videos today, and we'll be talking about voice over IP, what it is, a little bit about what it isn't, some misconceptions, and we'll be talking about how it functions, how it works, how it can be integrated into your network, and what its benefits are for you and your business. So let's get right down to it. Now, when most people think about voice over IP, the first thing that comes to mind is a technology which allows you to make a telephone call over the internet. So programs like Skype, WhatsApp, Viber, those are the kinds of programs that come to mind when you think about voice over IP. But voice over IP is not just limited to that kind of application. Voice over IP is something much broader than this. It's something that includes many more technologies and many more applications that are very useful for businesses today. Now, in order to understand where voice over IP exists on a network during a telephone call, I'm going to use a series of diagrams that will help us out. Now, when you make a phone call from your phone, whether it's an analog phone, an IP phone, whether it's a mobile phone, there is some part of the infrastructure that is using voice over IP. Now, here in this example, we have an enterprise which has an analog PBX, an analog phone, an ISDN line that comes into the premises, and that enterprise connects to the telco, the central office at the telco here, using ISDN. Again, this is not voice over IP technology. But from the central office down to the rest of the PSTN backbone, this infrastructure is all voice over IP infrastructure. Now, this is how voice over IP started to be adopted by the telephone providers. Now, there are still some telephone providers that don't have this voice over IP backbone, but for the most part, in most of the Western world at least, there is the backbone is over 90% voice over IP. Now, this was the first stage. This is where voice over IP was implemented as the backbone technology. From the central office on, we have the old telephony technologies such as ISDN and analog. Now, in this next scenario, we see voice over IP creeping its way more towards the end user. So here we still have the voice over IP infrastructure on the backbone, but we also have voice over IP infrastructure in the central office. The central office is the local node or the local location at which the wire that comes from your premises ends up at. So the wire on one end comes into your home or your business, and on the other end it goes to what is known as a central office. It is the point of presence of the telephony provider. So we have voice over IP technology in that point of presence, and voice over IP technology all the way to the enterprise. Now, this here is called the demarc or the demarcation point. And this essentially is the line, the border between the customer premises and the telephony provider. So up to this point, we have voice over IP technology. And here there's usually some sort of modem or CSU, DSU, where the voice over IP terminates. And then from here on, we have ISDN connectivity to connect the internal PBX, which is still legacy PBX in this case. Now, in this scenario, we see voice over IP technology creeping closer to the end user. So we have a VoIP infrastructure, we have a voice over IP central office, we have a voice over IP technology traversing the demarcation point. So all the way here, we have packets coming in, voice packets, and we have a PBX which has a port on one end that accepts a voice over IP trunk, and it is able to translate that into analog or ISDN signaling so that we can still use our analog phone or our ISDN phone on the premises itself. And finally, in this last scenario, we have voice over IP technology all the way through in the backbone, in the central office, the enterprise, the IP PBX, and we're ending up here with an IP phone, a phone that actually has an Ethernet jack that we can connect to, and packets, voice packets, come all the way here. This phone then reassembles the packets into a voice, producing the voice through the speaker on the phone so that we as humans can hear it and understand it. Now, this is an overview of where VoIP technology actually exists in a network. So we're not necessarily talking about internet here. We're talking about networks in general over which IP packets are sent. Now, this is a situation which is unfortunately relatively common. Depending on what part of the network is actually VoIP enabled, we may have a hybrid VoIP scenario. Now, in this case, we have the telco, which is providing a VoIP infrastructure here, and the VoIP does come all the way up to the central office, but the last mile, the local loop connectivity between the central office and the enterprise is only provided via ISDN-PRI, a traditional telephony technology. Now, we as a company, internally we may have said that we are going all VoIP within our company. So we have VoIP infrastructure inside the enterprise. But our telco cannot provide us with a VoIP trunk, but they can provide us with an ISDN-PRI. So here we have voice over IP infrastructure in our network, voice over IP infrastructure on the PSTN backbone, and an ISDN-PRI that connects us to the PSTN. Now, in this case, we need a voice gateway here, which will connect ISDN on the one end and a VoIP trunk on the other end in order to be able to do that translation. We'll get more into that a little later on. Now, the whole purpose of showing you these diagrams is to express to you where in a network voice over IP can exist. It's not just voice over the internet, but it is a technology that can exist in the PSTN backbone of a telephony network. It can exist in the last mile, the connection between the central office and the enterprise, and it can actually exist within the enterprise network itself. Now, in order for voice over IP to function, it uses a series of protocols. Now, a protocol in general is essentially a series of rules that are agreed upon by two devices on how they will communicate. So the first device says that this is how I will be transmitting my information. I'm telling you this so you can receive it, interpret it, and understand it so it can be useful information on your end. So voice over IP, like any other telecom technology, uses a series of protocols. Now, there are various protocols that VoIP uses, and among these we have signaling protocols, which are used between devices in order to control how calls are made. We'll talk about a bit more about that. We have media negotiation protocols and media carrying protocols. These are the protocols that actually carry the voice itself, the packetized voice itself. We have control protocols, which are used to maintain a certain level of quality. And then we have the underlying transport layer protocols, which are the protocols which are used in data communication in general, like TCP, UDP, and IP. Now let's talk a little bit about signaling in voice over IP. Now, it's interesting because signaling in voice over IP is very similar to that in more traditional telephony. That's because we come to know how telephones work. For example, whether it's an IP phone or an analog phone, they'll both ring. Whether it's an IP phone or an analog phone, when you pick up the receiver and you listen, you'll hear a dial tone or you'll hear ringtone. All these functionalities are called signaling. So if we have a telephone here and it's connected to some network, and this is connected to another telephone, and when this telephone goes off hook, when we lift the receiver off, a signal is sent from this phone and saying this phone is off hook. The system, whatever it is within the network, realizes this and is ready to receive the digits, the dialing. So we start dialing 175,394 and so on, the dial train. Those numbers are sent to a device known as an IP-PBX, and that IP-PBX receives those numbers, and based on those will route the call. Now, all of this uses signaling to take place. So then the call is routed, this phone is sent a signal, it rings, the person on the other end picks up the receiver, and an off-hook signal is sent, and essentially after all of that whole procedure, the phones are connected and the users can speak. So all of those tones, numbers, off-hook, on-hook, and so on, those all involve signaling. Whenever an event happens, a signal is sent. Here we have an example of an IP network where we have an IP-PBX, and we have two IP phones, and we have what's known as a SIP trunk. Now a SIP trunk, we'll talk a little bit more about SIP. SIP is a control protocol. A SIP trunk is essentially a connection to the PSTN provided by a telephony company. So when you have an IP-PBX in your premises and you want to connect to the PSTN via voice over IP, they will give you a SIP trunk which will connect to your IP-PBX, and all calls will be made through that SIP trunk to the PSTN. Now here we see a call being made between these two IP phones. So when this first IP phone picks up the receiver, an off-hook signal is sent to the IP-PBX. The IP-PBX responds and says, play dial tone. So the phone plays dial tone. The dial tone tells the user that it's ready for the digits. Now, all of this communication that takes place between the phone and the IP-PBX uses the SIP protocol. SIP stands for Session Initiation Protocol. Now, once we hear the dial tone, we start dialing the numbers, and these numbers are sent to the IP-PBX using SIP. Once all the numbers are dialed, the IP-PBX says, okay, I know where this phone is. This phone has an IP address of 172.33.75.7. And that PBX sends that IP address to this IP phone and says, this is where you can find this device. So then this IP phone, knowing the IP address, sends a SIP signal directly to the other IP phone, to the destination. This IP phone receives the SIP signal and begins to ring. Once that phone is off hook, the off hook signal is sent back to the IP-PBX saying that I'm off hook, and then the two phones begin communicating. Now notice here that all communication, all voice communication, which are, let me get rid of some of these lines so that it'll be clearer. All the voice communication between the two phones takes place directly between the two phones. It doesn't go through the IP-PBX. Now, this may be a bit strange because traditionally, analog phones which connected to a PBX, all of signaling and voice and everything goes to the PBX, and then it's sent from the PBX to the destination. Here we have signaling between the phones and the voice packets between the phones going directly between the phones. The PBX is not involved at all. The only thing the PBX does is just monitor the state of the two IP phones, which is these green lines here. Monitor the state of the IP phones so that it knows that they're busy. If there's another call coming into them, that it will, the IP-PBX will return to that third caller the fact that the line is busy. So the important thing here is that SIP is the protocol used for signaling. SIP does not actually carry the voice. SIP only allows VoIP devices such as IP phones and IP-PBXs to communicate with each other so that they know what is going on. They communicate things like ringing, things like tones, things like numbers being dialed, off hook and on hook, and all of those are sent using SIP. Now the actual voice packets, when we speak into this phone, the voice is digitized and then it's packetized and then it's sent over the network. All of this will go directly from phone to phone. And that uses another type of protocol. So SIP is the control protocol used for IP devices to communicate with each other and coordinate the creation and teardown of telephone calls. So in this scenario, we have the control protocol, which is SIP, and then we have the media negotiation, media carrying, and control protocols, all taking care of sending and receiving the actual voice packets. For those of you who are more network minded, you will realize that what we have here on the left, this stack, is the OSI model, or the Open Systems Interconnect model. This is a model for network communications in general. It is a model used to describe network communication. Now, SIP, SDP, RTP, and RTCP are 4 voice over IP protocols, the 4 major voice over IP protocols, which are used in order to allow VoIP to function. TCP and UDP are 2 transport layer protocols which are widely used for all network communication. So SIP and SDP, which are 2 companion protocols, SIP is the control protocol, SDP is the session description protocol. These 2 work together in order to allow voice over IP devices to communicate with each other and create and tear down calls. RTP and RTCP are the real-time transport protocol and the real-time control protocol. These 2 protocols are used. RTP carries the actual voice packets, while RTCP monitors the session, and if there are any quality issues, it will inform the devices communicating, and they may and can adjust their several parameters in order to be able to improve the quality of the session. Now, SIP and SDP can use either TCP or UDP as their underlying transport layer protocol, while RTP and RTCP will almost always universally use UDP for their communication purposes. So just as a summary and a further clarification, if we have an IP conversation between an IP phone and a soft phone, for example. Now a soft phone is just an application on a computer that functions as a phone. Now if we have a communication between them, we don't only have one session between them, but we have several sessions. The first session is SIP, which is a signaling session, which, as we said, allows for the actual calls to be created, set up, and torn down. We have the session description protocol, which helps in the control of that communication. And then we have 2 more sessions. One is with RTP, which actually has the voice payload, the packets, your actual voice that is digitized, and RTCP, which provides statistics and control to the devices in order to allow them to modify any parameters necessary to maintain or improve the quality of the communication. So those are the protocols, the most common protocols used for voice over IP. Now I just like to mention that although SIP is the de facto standard today for many vendors and voice over IP providers, there is another standard called H323. This standard is also a voice over IP standard, which also uses RTP and RTCP. It's very closely modeled after the ISDN technology, which was the original digital voice technologies that emerged in the 70s and the 80s. And this is a whole other protocol suite that is used by many vendors and is particularly used by both video conferencing systems, leveraging voice over IP, as well as very large enterprise networks where there are many different sites throughout the world. So companies that have headquarters, regional headquarters, they have branch offices in many different countries all over the world, maybe hundreds or even thousands of locations. H323 is a protocol that is very useful for very large hierarchical networks such as those. But we won't mention H323 anymore. SIP is by far the most commonly used and, according to some, the most powerful VoIP control protocol available today. Now, a very important concept for voice over IP is how we get the voice, which is essentially a sound, into a form where it can be transported over a network using packets. Now, in order for voice to be carried over an IP network with the protocols that we described so far, it must be digitized and subsequently packetized. Now, the human voice is analog by nature. Digitizing voice means that we can represent it using ones and zeros. This is done by capturing the sound using a microphone, such as that found on a telephone receiver, and using various algorithms to convert it into digital form. Now, in order to understand digitization, let's take a look at an example of what sound is and how it's represented. Here we have a graph that shows one particular aspect of a sound, and that aspect is volume. Let's say we have a sound that is increasing steadily in volume. Now, as we can see over time, the curve increases. Now, if we were to take a very small portion of this curve, of this increase in volume, over a very small period of time, let's say several microseconds, if we were to zoom in and look at this here, this portion of the curve, we'd see that the curve continues to be smooth. Now, this is what analog means. Analog means that no matter how close you zoom in, no matter how small you make this delta t, this time interval, you will always see a smooth increase in the volume over time. So an analog phenomenon, which is all phenomena essentially in life, color, sound, movement, everything we see and do is analog. Analog phenomena essentially have a smooth curve when we describe the way they operate or function or change. Now, when we look at something that's digital, first of all, we must understand that the digitization of something means that we're not actually changing its nature, but what we're doing is we're representing it using binary. So when we take this sound, this increase in volume over time of this sound, and we digitize it, what we're doing is we're representing the curve, we're representing the change in volume over time using a binary, using a digital format. Now, what this does is it changes the form of the curve in such a way so that it goes up in steps, because digital representation can only represent things at very discrete, specific values. These values in between do not exist in the digital realm. So if we were to digitize that increase in volume, what we'd see is a series of steps. Now, if these steps are close enough, we can represent this increase in volume more accurately. If they're not that close, then the representation is not very accurate. In any case, no matter how accurate the representation is, if we take a change in time, delta t, small enough, we will eventually see that the change in volume between those two times is zero. So digital representation means that it is represented by discrete, specific values, and it's not a continuous curve like an analog curve would be, like an analog phenomenon would appear to be. Now, the more steps we have in this representation, the better the representation is. And we come to a point where if these are small enough and if these occur often enough, then we as humans, when we perceive this representation, will see no difference in it compared to the original. Now, when it comes to digitization of voice, there are two very important aspects that we must keep in mind. The first is called the sampling rate. Now, the sampling rate is the frequency at which sound is sampled or recorded. Now, because a digital representation is one with discrete values, with discrete samples, the higher the sampling rate, the higher the quality of the sound. And each sample of sound is represented by a set of bits. Now, the sampling rate is measured in hertz, and this is a measure of frequency. It's the number of samples per second of a sound that we take in order to digitize it. Now, the other concept that's important here is what's called bit depth. And the bit depth is the number of bits that are used to represent a sample. The more bits we use to represent that sample, the more accurate the representation is. Now, some examples of sampling rates and bit depths that most of us are familiar with is CD quality sound. CD quality sound is sampled at 44 kilohertz, which is 44,000 times a second. And the bit depth of most CD quality sound is 16 bits. So that means that we are recording sound 44,000 times a second, and each one of those little recordings, each one of those samples is represented by 16 bits. That means every second of sound that's recorded or sent over the network will have a size of 16 bits times 44,000 per second. That's 704,000 bits, which is 704 kilobits, which is approximately just under 90 kilobytes of data. So CD quality sound will take up 90 kilobytes of data for every second that it plays. Now, by playing with these values of 44 kilohertz and 16 bits, raising them, increasing them, decreasing them, we can have representations of sound that become more or less accurate, that become more or less true to the original. Now, to understand sampling rate a little more clearly, let's take a look at this red curve. This is a red curve that represents a sound wave. Now, each blue dot is a sample. So during that sound wave, as it goes through the air, hits a microphone, and the microphone converts it into analog electrical signals. This comes to a digital signal processor which does the sampling. So at every time interval, at every sampling interval, we take a sample of the sound. So at this point, we say the sound is at level 8. At this point, level 9. At this point, level 11. At this point, 13. And so on. So we essentially get a series of numbers: 8, 9, 11, 13, 14, 15, 15, 15. And you can see that these are just these numbers here. And each of these is represented using bits. So 8 is in binary 1 0 0 0, 9 is 1 0 0 1, 11 is 1 1 0 0, and so on. So we get a stream of bits which can then be which can then be packetized and sent over a network. Now we see that each sample is 4 bits. So we have a bit depth here of 4, and we have a sampling rate let's say that this is 1 second here. 1 second from here to here. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So let's say we have a sampling rate of 12 hertz. Now, 12 hertz would be way too low to actually represent a real sound, but for the purposes of understanding digitization, let's just use that value. So we have a sampling rate of 12 hertz and a bit depth of 4 bits. Now, you may notice the higher the sampling rate. So if we have a sampling rate, if we sample here and here and here and here and all the way along more densely than we would at 12 hertz, let's say at 24 hertz or 30 or 40 hertz, then we can see that we gain a better representation of the actual curve because we have more information about that curve and it can be sent over the network. But there's a problem here because we can only have values, integer values, 9 or 10. We can't have 9.5, for example, or 12.4 here, for example. We need to have either 12 or 13, which means that if I want to sample this location here, what am I going to make it? Am I going to make it a 6 or a 5? I don't know. I'll make it whatever's closest. Let's make it a 6. But that means that the sound quality will decrease. So what do we do then? Let's increase the number of values. So instead of having values from 0 to 15, let's have values from 0 to 255. That means we're using 8 bits per sample. So that means that we'll be able to get more accurate values for representations such as this here. So bit depth allows us to recreate a higher bit depth allows us to recreate the curve more accurately because we have more values in the y-axis that we can define, and sampling rate allows us to have more samples in the x-axis so that we can more accurately represent this curve. So the result will be a representation in digital form that is more accurate to the original. So when that reaches the other phone on the other end, when it's converted from digital back to analog, which is sound, which is the way we hear things, then its conversion will reproduce something much closer to the original. So that's bit depth and sampling rate, and why those are very important when we are digitizing voice. Now here we'll see another example of how bit depth makes a difference in the quality of a sound. Here we have a sound wave. This is the original sound that we see, and we can use various levels of bit depth in order to represent this. Now we're going to the extreme here just so that we can understand what that means. If we use 1 bit to represent this sound, that's a 1 or a 0, then we have value either 1 or 0. So this square wave here will represent that original sound. We can see that that's very little like the original sound. There's very little in common between those two. Now if we were to use 2 bits to represent this sound, the bit depth of each sample, then we would have 4 possible values: 0, 0, 0, 1, 1, 0, and 1, 1. And each of those would represent one level here. So we see that the wave looks a little clearer to that, but it's still quite blocky. Now if we were to use 4 bits, that would give us 16 values all the way down here. So all of a sudden, it looks a lot more like the original. And if we were to use 16 bits, then from far away, we can see that the curve is very smooth. It looks identical to the original sound. But if we zoom in, we can see the stepwise manner of its representation. So the bit depth will give us more bits to represent each sample, thus representing and recreating the original sound more accurately. Now, once the voice is digitized into small samples of several bits each, that information can then be sent over a network. It can be packetized and then sent over a network. So it can be broken down into small pieces, placed within IP packets, and then these packets are encapsulated into RTP datagrams using the RTP protocol that we described before. And they're sent over the network according to the signaling information that is provided by SIP. Now, the method of digitization and packetization, all of these things that we described so far, are standardized within what is known as a codec. Now, codecs, or coder-decoders, are standardized methods of encoding and decoding voice. Now, codecs define how a sound is digitized, how it is packetized, and each codec also defines sampling rates, bit depths, digitization, and even compression algorithms that will improve the transmission. And it also defines the packet sizes, the size of each individual voice packet that is sent over the network. All of these varying parameters that are defined within each codec result in each one delivering voice in a different way, with varying qualities, with varying rates, with varying bit rates and efficiencies. So you have to choose the right codec for the right application. Now we'll go through a few codecs that are very common in use. We have the G series codecs, which are defined by the ITU, the International Telecommunications Union. The G711 codec is arguably the most mature and widely used codec today. It matches toll quality voice, so if you hear voice on an older analog or ISDN connection and you hear voice from G711, essentially they'll sound exactly the same. And it is supported by the vast majority of vendors, IP PBX vendors, IP telephony vendors, voice gateway vendors, and so on. Typically, sampling rates are at 8,000 hertz, 8 bits of bit depth at a bit rate of 64 kilobits per second. Now, it's important here to note that the 64 kilobits per second matches that of one ISDN channel. And this is because G711 was based on that ISDN technology, the digitization of voice using that technology. The payload size per packet is at 160 bytes. There's no compression by default. And the MOS, which is the mean opinion score, which defines the quality of the sound on a scale of 1 to 5, is 4.2. And that's approximately the same as toll quality voice. Now, G729 is another ITU-based protocol. It has an extremely low bit rate because it uses compression. So instead of a bit rate of 64 kilobits per second compared to 711, we have a bit rate of 8 kilobits per second here. That's a huge decrease. That's 1/8 the bit rate used. And the payload size is at 20 bytes, a very small packet size for this here. But notice how the bit depth increases. Because we have compression, the decrease in quality due to compression is offset by the increase in quality that's provided by the bit depth. Now, the MOS score here is 3.9 compared to 4.2. That's not too bad. The most common usage for G729 is to be used over lower bandwidth links, and typically those are WAN links between headquarters and a branch office, which typically are more expensive to get higher bit rates. So 729 is used for much smaller bandwidth links. Now, the G-series codecs that we saw before are defined by the ITU, International Telecommunications Union. Now, they're the ones that have also defined all of the analog and ISDN and traditional telephony protocols in the past. So their VoIP protocols look very familiar, look very similar to the protocols used in traditional telephony. Here we have a couple of codecs that have been developed by the Internet Engineering Task Force. Now, this is a whole different approach to how to do voice over IP. Now, and it's a different approach because these are coming from an internet and IP background, so IP data background rather than a voice background. So it's a different approach, it's a different way of doing things. Now, these are actually quite impressive because we have, for example, on the ILBC, we have a sampling rate of 8 kilohertz, a bit depth of 16 bits, and we have a bit rate of 13 to 15 kilobits, which is actually quite excellent. The payload size is variable. We do have compression in order to get such small bit rates here, but we do have an MOS of 4.1, which is slightly better than the G729. And then we have Opus. Now, this is an extremely flexible and configurable codec. This is an open source codec. It has a wide range of qualities with very small bit rates. It's used not only for IP telephony, but it's used for general sound recording, for audio recording, music, for the recording of audio as a part of high definition video as well. Now notice here we have bit depths that go up to 32 bits, which is extremely high quality. And we have bit rates which are very low for those kinds of sampling rates, 50 hertz, 20 kilohertz, which is essentially the full range of human hearing. And we have a payload size that varies depending on what all of these qualities are. And we have an MOS score of somewhere between 4 and 5, depending on what kind of characteristics we have here. So Opus is actually one of the most versatile that are out there, although it's not supported that much by voice over IP equipment and vendors, although that is slowly changing and it is being supported more and more as time goes on. Now here we have a graph which describes the quality of various protocols and compares it to their bit rates in kilobits per second. So there are various qualities and various categories that we can see here. The narrowband protocols are those like G711, 729 is in there as well. We have ILBC, which we saw before. Those are protocols which provide essentially telephony quality sound, that tinny sound we get when we hear people speaking over the phone. And essentially it's called narrowband because it has a low sampling rate, 8,000 hertz typically. Then we have the wideband, super wideband, full wideband, and full wideband stereo, which essentially what this does as we go higher in quality, it's an increase in the sampling rate that we have, and also an increase in the bit depth. Now we see here that Opus has so many different, it's so flexible and has so many different variables that we can adjust, that we go from very low bit rate and quality all the way up to very good quality up here, full band stereo, using only 128 kilobits per second, which is actually quite impressive. Now MP3 is up here as well, so it gives you an idea of what kind of qualities we're talking about. G722 and 722 here, which are two ITU wideband protocols used, and 719, which is used in decked cordless phones as well. So you see, and there are many other protocols that can be used and are being used for sound. Now the important thing to notice here is you have to choose the protocol which, one, is supported by your equipment, two, provides you with the quality that you need, and three, can be run over your network with the bandwidths that are available on your network. So you have to balance these out and find out which one will fulfill these three requirements in the best possible way. And you can experiment with that on your network. But in general, for telephony, we see the use of G711, ILBC, and sometimes G722 are the most commonly used. And you see that they do provide good bit rates for the quality that they provide. Now in this video we talked a lot about the theory behind voice over IP. We talked about protocols that are used, we talked about codecs, we talked about where on the network VoIP actually exists and how it functions. And we also spoke about digitization, sampling rates, and bit depth. Now, this is all required theoretical knowledge in order to go to the next step and understand how all this comes together, how all of this is actually implemented on a network. In the next video, we'll be talking about VoIP components, IP phones, gateways, IP servers, SIP trunks. And we'll see how all of these components come together and use this fundamental theoretical background in order to be able to function and offer you and your business everything that you need. I hope that all of this has been informative for you, and I hope that you'll join us in the next video so that we can continue our journey looking at voice over IP. Thanks for watching.